Okay, everything seems to work, I hope. Okay. So thank you for inviting me here. It's a pleasure to be in Granada again. So so my talk is going to be on univariate, only univariate, and I guess the conference is on multivariate, but to understand multivariate, you also have to understand univariate, right? So let's see. So my talk is, I'll start talking a little bit, mention least square curve fitting, and then a little bit of smoothing splines, a B-spline using the recurrence definition, not divided differences, and something which maybe some of you don't have seen is to introduce B-spline using so-called matrix products. And then see how we can represent polynomials of B-splines. There's something called the control polygon, which is important in the geometry for B-splines. And then I end with talking about knot insertion and something called the Oslo algorithms. So let's see. So the basic here, we have two bases for univariate polynomials. You have the usual power basis, 1x to the x to the n, and then you have the Bernstein basis, which we're going to hear a lot about in this talk, but I mentioned it here. So this is, as you see, for some of you maybe haven't seen it before, then it's about time. So you have, for example, in the quadratic case, you have B0, 1 to the x squared, B1, 2x, 1 minus x, and B2, x squared. And this basis is nice. It's positive on the interval 0, 1, and it forms a partition of unity. I mean, it's summed to 1. So we should think about our Pn as a finite dimensional linear vector space of functions, and it's dimensioned in it's n plus 1. So in curve fitting, the way I present it here is that you're given m values, mx values, and my values, and the x values lies in an interval a, b. And the problem is to find a smooth function, g, which approximates, so g of xi is approximately a yi. And so we have, so for the curve fitting, what I will mention here is just to recall least square curve fitting. You have something called smoothing splines. And I will not talk about something which some of the statisticians maybe know about kriging. But this, well, we might maybe hear about that. So least square fitting is the way I present it is you're given a set of basis functions, B1 to Bn, and typically we are basis for the polynomials of degree n minus 1, since I don't start with 0. And the function space is all linear combinations of these B-splines. That's and the linear least square regression is to find coefficients C star and the function in the function space, which minimizes the yi minus the sum of bj xi cj squared. And as I just mentioned, that you can find C star by solving a linear set of equations, A transpose A C star equal A transpose Y, which are called the normal equations. And A is this is collocation matrix with the basis functions evaluated at the xi's, right? And this is normal equation, they always have a solution, and it has a unique solution if and only if A has linear independent columns. And if you want to, one possibility is to look in this book, Numerical Linear Algebra and Matrix Factorizations, which explains the background, the linear algebra background for these things, and also talks a little bit about curve fitting. And there's a companion exercise book, which with Georg Munting and Øyvind Ryan, which have solution to all the exercises if you want to study this. So that's So let's start to have polynomial regression. So linear regression, you want to fit, of course, a straight line to some data xi, yi. And the space is n, for example, the polynomials of degree n-1. And we know that the normal equation have a unique solution if and only if x has at least n distinct components. So it's a very weak condition for that. And if you have more than n is bigger than 2, you have more than 2 basis functions, then you would fit a polynomial if the data is not, if you don't want a straight line, it makes sense. So what I will talk about now is smoothing splines. So combining data smoothing with splines. So as in many cases with splines, the first article is by Schoenberg, which has, for if there's any students here, has a funny title, Spline Functions and the Problem of Graduation. And so it was an algorithm by Lyche in '67, and it's a paper with my first paper with Larry Shoemaker, my supervisor, was written in 1973. This was using natural B-splines for computing smoothing splines. And I will also mention this book by Grace Waba, which I'll come back to. So what is a spline? So here's a picture of a physical spline. So it consists, a spline in the physical sense is a flexible beam, typically could be of wood or plastic, is kept in place using ducts. And these big loads here, which they're quite heavy, but you can move them so that you can get, for example, if you want to make an S, this is how you could do it with this thing. And the shape of the physical spline will be that it try to minimize its potential energy, and the potential energy is somehow related to the minimal curvature of the function. You have to do some integration and stuff. But what we usually do is to, instead of minimizing curvature, we're minimizing second derivative. So that's what we will do here. So so a smoothing spline, you typically have then n basis functions, which typically could be B-splines, and you want to find a function, a linear combination of the basis function, which minimizes both the sum of the least square minimizing plus a spline term minimize a constant alpha times the integral of the second derivative square. So that's what typically is called a smoothing spline. And I will not go into details here, but say that at C alpha, which is the minimum of this function, can be found as a solution of a banded linear system. For example, you could look at my first paper with Larry Shoemaker where we show that. But the question I'm interested in here is not so much how you solve it, but how can we solve alpha? How should you solve alpha in the smoothing parameter? And there's a technique which was explained in this book by Grace Waba called cross-validation. So suppose you are given a guess for alpha, but you want to find a better alpha, I mean, a combination for your smoothing. So then what you do, instead you find some functions, CKI, which minimizes the smoothing term, I mean, the least square term plus the smoothing term, but you avoid, you don't use the ith you don't use the ith term here. So this in a sense, this G yeah, is a prediction for yi using this alpha. And then you can define a cross-validation function by summing, see how well this G minus I here approximate the ith data point, because you haven't used that one, right? And that's so you want that's a cross-validation function, and the cross-validation is to minimize this function given us, which gives us what is called the cross-validation value for alpha. And the minimum might not be unique. And it says, so usually they recommend using some kind of a grid search to find this alpha, cross-validation alpha. Okay, so that was just a very brief talk about cross-validation. So now I turn to B-splines. So the B-splines are the two classical books on B-splines. It's one by Carl de Boer and one by Larry Shoemaker. And they both appeared around 1980 and have been updated now in de Boer's book 2001 and Shoemaker's book 2007. But the sort of the original paper which introduced general B-splines is a paper by Curry and Schoenberg from 1966. And this paper is based on divided differences. They introduced B-splines using divided differences, which I will not do here. But what I will do is I will base the B-spline part of this lecture is based on some lecture notes by my co-author Knut Mørken, and you can download it. There's a link here, which you can download it for free. It's a lecture notes. It's about 240 pages long, which have been used to giving spline courses in Oslo for 50 years. And so, okay, so what is a B-spline? If some of you have never heard the word or have no idea what a B-spline is, so here's an example, a quadratic B-spline. So to define it, it's defined by something called knots. And in the quadratic case, I mean piecewise quadratic function, it has 4 knots. And here's an example. The knots are 0, 1, etc. And the degree now is the number of the B-spline is the number of knots minus 2 in the univariate case. And so here is a picture. The B-spline is this blue curve here, and it consists of 3 pieces of parabola. And here you have a 0, then you meet this red or pink parabola, and you see it meet here, so it's smoothness C1 right here, and then you meet the yellow parabola here, and they meet exactly at the point where you have the knot. So you have the same tangent, so it's C1, and then you use that yellow until you meet the green parabola, and then etc. So you can say that, so it has smoothness C1, and it's a piecewise polynomial function. It could be, there are many generalizations of this. It doesn't have to be piecewise polynomial. It could be piecewise any kind of set of functions, like, for example, what we call Chebyshevian splines is active research area in this field. And you can see that the blue curve, it's sort of bell-shaped. It looks like a kind of a normal distribution, but it has finite extent, I mean, what we call local support. That's the difference, and and it has pieces of polynomials, right? Okay, so so here is the recursive definition of B-splines. So you compute the B-spline, the jth, what they call the jth B-spline of degree p, as a linear combination of two B-splines of degree p minus 1. And you have certain coefficients here, which I will not spend too much time explaining. I mean, they do divide by what's called the support of the B-spline in the denominator. So in here, as x is this definition is for all x in all real x. The knots Cj to Cj plus p plus 1, they are non-decreasing. And can have, many of them can be equal. So then you say that the multiplicity with respect to Bj of some Xi is a number of knots of Bj which are equal to Xi. And then you have another interesting fact that you somehow the denominator can be 0. But if the denominator is 0, then also the b corresponding b will be 0. So then you have 0 over 0. And if you have, so if the denominator is 0, this term is not there. It's 0. So that's the sort of the full definition of a recursive definition of a B-spline. And but to start, I mean, this is recursive, so you have a degree p. You need to know degree p minus 1. So you have to start somewhere. So you start with p equal to 0, and bj0 is equal to 1 if x is in the between Cj and Cj plus 1 and 0 otherwise. And we use sort of here the half-open interval, as you notice, so that the value of a B-spline at the knot is obtained by taking limits from the right, what's known as a right continuity. So in particular, on the at the Cj plus 1, this you see that the bj0 will be 0. So it's always 0 at the right endpoint in this, according to this definition. But sometimes we need it not to be 0, and then we can use left continuity at that point, Cj plus p plus 1, taking the limit from the left. So, but normally we use right continuity to define the B-splines. But that's just a choice, right? It could be, yeah, otherwise. Okay, so let's just give one or two couple of examples. Here is degree 1. If the Cj, j plus 1 and j plus 2, they are the three not defining line, and you get from the recurrence relation, you get this kind of piecewise linear function here between, for example, here is the knots are 0, 0, 1, 2, and 3. So then 0, 2, and 3, and you get this function. And but there could be multiple. So for example, this Cj and Cj plus 1 are equal, then the value there is, then you get the 0 over 0. Have to use the 0 over 0 convention, and you only get this one term here, which gives you this straight line here. So it's equal to, will be equal to 1 here and 0 over there. So that's a piecewise linear case, which you can compute using the recurrence relation, if you don't want to use a simpler explicit form. So there are two special cases of B-splines which occur frequently. This is what is called cardinal B-splines or uniform B-splines. That's MP is a B-spline where the knots are 0, the integers 0, 1 to p plus 1. And then we can define for each j, integer j, we can define bj as a translate of MP. Right? And another important example is the Bernstein basis polynomials, is also a B-spline, actually. You can get it by taking a certain number of knots at 0 and a certain multiple knots at 1, and you get all those basis function as B-spline. Okay, so what about the smoothness in general? Well, the one thing to remember is that the smoothness of a B-spline is a degree minus multiplicity at the knot. This is sort of the thing to remember. Degree minus multiplicity is smoothness. What does it mean? For example, here is an example, quadratic. You have knot Cj. You have two knots, Cj plus 1, which are equal, and one here, simple. And then the smoothness is degree. Here is degree 2. So the 2 minus simple multiplicity is 1. So smoothness is C1. In the center here, degree 2 minus multiplicity 2 gives us C0. And similar here, get C1 at the simple node. So this is how you, and you only use the knots of the B-spline to define the multiplicity in this case. Okay, so now, but one B-spline is fine, but what can you do with one B-spline? So look at it and see, oh, how nice it looks. But but you need so you need a collection of linear combination of B-splines to do anything. So suppose now so in this case we have suppose now we have instead of having p plus 2 knots for one B-spline, we have n plus p plus 1 knots. So if n is 1, we have one B-spline, and then for n bigger than 1, we have n B-splines. It can be defined here in the following way. Well, let's assume for that Cj plus p plus 1 is bigger than Cj. So each B-spline has extent, and in many cases it's very convenient to consider what's known as an open knot vector. And an open knot vector means that the p plus, if you have degree p, the p plus first knots are equal, and the p plus 1 last knots are equal, and then and the other one are sort of inside. So that's typically could be an interval A, B here, and these are interior knots in the interval. And then we can define a spline space SPC, which splines of degree P on the knot vector Xi, which is then this one up here, and its function, which typically is because of the right continuity, is kind of defined on the half-open interval Xi1 to Xn plus P plus 1, and as a linear combination of these B-splines, n B-splines, which you can define on this. And if Xj plus P plus 1 is bigger than Xj, these functions will be linear independent, particularly on the open knot vector. So it's a function space of dimension n. These functions are linearly independent. And you can also, as we will see later, that these B-splines form a partition of unity. They sum to 1 at every point x in the point. So this will. So here's an example of how this can look. Suppose we have an open knot vector. I usually use quadratic as examples in my talk. You have 3 knots at 0, 3 knots at 4, and 1, 2 interior knot 1, 2, 3. So the P, you have P is equal to 2, and you have N is equal to 6. 1, 2, 3, 4, 5, 6. You don't count the last P plus 1 knots when you count the dimension, right? Or many B's. So here's how they look. The first one, which has not 0, 0, 0, and 1, will look like that. It would discontinuous at 0. And then you have the 4 interior B-splines here and the last one up there. So this is typically a collection of B-spline. We look at, in this case, there are simple nodes in the interior. Okay, so now let's get to how can we compute with B-splines? So so usually you consider now one subinterval. I mean, it's a piecewise polynomial on each subinterval, right? So you take the ones which belong to one subinterval and see and the point x in that interval. How can you find the values of these B-splines in that subinterval? I call it Cj plus 1. And so the way I'm going to do it is the way we do it in that notes with Merkin. We define B-spline matrices. And well, first, because of the local support, there's only p plus 1 B-splines, which can have a non-zero value at that interval. Xc nu minus p to Xc nu. And it's possible to define explicitly all those these p plus 1 B-splines for general p as a product of matrices. And so we start with R0 equal to 1. And then that gives us if this p was 0, this will just be R0. And then that's the definition I had before for degree 0. If p is 1, R1 would be the two pieces of the B-spline. I mean, the one going up and the one going down, right? And in general, you have for any k, you get this in this here Rk somewhere. It's a k by k plus 1 matrix, and the values of that it's computed comes from the recurrence relation. You can compute. I'm not going to go into how you find it, but you can look in the book, in the lecture notes. And so it's a k by k plus 1. So for 1, so it's 1 by 2. And the numbers explicitly are here. So if you compute all this product, you have explicit value of all those p plus 1 B-splines at the point x in that interval, right? Explicitly. So and this matrix, as you can see, is bidiagonal, has just two diagonals. Okay. The one very important property of those B-splines for the theory, which we will develop a little bit, is something called symmetry. And the symmetry says that if you take any 2 points in R and any k, and you evaluate take the product of Rk at evaluated at x and Rk plus 1 evaluated at z, it's the same. You can switch z and x. So you can take Rkz times Rkx, and you get the same value. And this is sort of the basis for getting a lot of the algorithms and things. We also will consider to take derivatives of B-splines. We need some derivative matrices, which we call drk, and which are also, and they are obtained from rk by replacing all numerators by minus k and k. So if you go back, you see, you take this, here you have a minus x, you take the derivative, or then you get the minus 1, but instead of taking minus 1, you take k, minus k on this, and plus k on this one. So it's a minus k down here and plus k over there. That's the derivative matrix. And then, so if you do, then you get this symmetry relation for the derivative drk can be sort of switched at x and z. You can switch x and z also for and the derivative, when you take a derivative with respect to x. Derivative with respect to x, derivative with respect to x, but here's k plus 1 in this case. Okay, so that's this B-spline matrices. So using that, now we can derive, now we can have an explicit formula for finding the rth derivative and the derivative of all those B-splines which are non-zero on that interval Cj. So let me see. So the formula says that you take the first, you have rth derivatives, you take the first p minus r matrices at x, and then you take the remaining r B-spline, you use the derivative matrices like that. So this is a formula for any derivative of those B-splines. So let me just indicate to you how you show this. So let's look at the first derivative. Suppose you want to find the first derivative of those p plus 1 B-splines. So then you use the product rule. You take, then we take the one with r equal to 0, so you have r1 to rp, and you differentiate the sum of the jth. You take the derivative of the jth term, right? And then you use a symmetry. You can split. You can exchange the rj with x with the rj plus 1 of x, and switch the order. So in this way, you can put all the derivative terms at the end. And then you have p, then you have a sum of p terms, so you get the p here. So that's why you get this minus k and k, because you have a p, you get this p here, and I don't want to bother with this fact. You could put those factors outside, but it looks neater this way. So then you get this formula for r equal to 1, the first derivative. You have p minus 1 matrices at x times the derivative matrix or the p, like that. And if you continue taking derivatives this way, you get this general derivative formula here. Okay. Okay, so then you can, so then you have this formula, algorithm for computing the values of a spline on the subinterval. Suppose you have a linear combination here of B-splines, and if you are in this interval, you have just this j from nu minus p to p, and then if you want the rth derivative, you take those, use the derivative formula p minus r, rk up to p minus r, and the derivative, and then you multiply by the coefficients here, which are involved in this sum, c nu minus p to c nu, and the transpose, because I consider this as a column vector. Okay, and for r equal to 0, then you have no derivative term. This is known as the Bohr algorithm. Some of you maybe have heard that name. And then you have no derivatives. And you can see that what's the complexity of this formula? Well, each of the matrices are bidiagonal. So if you multiply, so if you multiply that for any r, you get an algorithm require order p square arithmetic operations. And where we accumulate from the right, we start with the c, then multiply by the first dr, and go down to 0, right? This is, and for r equal to 0, this kind of combination, this involve only convex combination, so they're kind of numerically stable as such. I mean, meaning the c's could have different signs, right? But so this is sort of the algorithm. So now we know how to compute the rth derivative, any derivative of any collection of B-spline at the point X. Right? So in this way. So let me just break with the pictures here. Well, B-splines go back, was already mentioned by Laplace in the book on statistics in, I think, around 18 or beginning of the 19th century, 1802 or something like that. And then there were some Bulgarians and Romanians who actually developed almost all we know about B-splines in the 1930s. They did the recurrence relation, which was later discovered in 1972. And there were, and Marston identity, knot insertion. They did it all, but it stayed in Bulgaria and Romania. Nobody, so it was not known in the international community. But there's a very nice book, article written by Carl de Boer and Pincus which explains the history of this B-spline. This one is interested in history. So this is Popoviciu and Chakalov. Okay, so now let me talk about how do you, it's fine now we know how to evaluate, but suppose not B-splines and in a derivative, but how can we approximate with them? And if you need to approximate it, it's good to know how can we represent a polynomial in terms of B-splines. And we can. I mean, it's maybe not obvious because they're all kind of bell-shaped functions. How can we, for example, solve them to get a straight line? We need to know which CJs do we choose to get a straight line, for example, or if you want to get x squared, how do we find the CJ? So that's what I'm going to explain now. The way I'm going to do it is via what's known as dual polynomials. And dual polynomials is a polynomial of degree Cj of degree p is a polynomial of degree p given by has zeros at the interior knots of Bj. So you take the p interior knots, you don't use Cj or Cj plus the first and the last one, only the interior knots. It's a polynomial of degree p, and you know the zeros, right? It cannot be more explicit than that. So this is what we call the dual polynomial corresponding to Bj. So each Bj has its dual polynomial. And it's interesting, for this dual polynomials has a recurrence relation, which is, well, for B-splines, we increase the degree, went from p plus minus 1 to p. In the dual polynomials, we reduce the degree. We go from degree p to degree p minus 1. And here it is. Let's see, we have, so again, we'll consider an interval, c nu plus 1. And we have, we take all the vector, column vector ck with the k plus 1 dual polynomials at the point y, and y could be any sort of point, fixed point. And then if we take this kind of column vector here, multiply it by the pth matrix, we get those of degree 1 lower, but with the factor y minus x in front. And that's what they call the dual recurrence relation. So let me just indicate, since I have a few minutes, I guess, to how do you show that, because this is sort of the basic. So first, suppose do we have something I call the dual recurrence lemma. Suppose now we have a Xi to Xi plus P in non-decreasing, and then that the Xi plus P is bigger than Xi. Then we have this relation here that the linear combination of the ith dual polynomial, I minus first dual polynomial, is y minus x times a dual polynomial of degree 1 minus 1, p minus 1. And this formula is just linear interpolation with the function g of x equal y minus x for a fixed y. So if you do linear interpolation and you have the g of xi plus p times this term and this term, and then you get g of x. That's a linear interpolation. Anyway, this is, so if you know linear interpolation, you can derive anything you want on B-splines, actually. So this is, and if you multiply and take this relation here and multiply by CIP minus 1, completes the proof. And of this recurrence lemma here, where you get it. Here you just had one y minus Xi plus P, right? And then you take the remaining you need for the Xi's, and then you get the proof. Yeah. So this is okay. So then we get now we have that, and we have something called the Marsden identity, which is sort of what the tool we can use now to how to represent any yeah, I have problems talking, I guess. I wanted to say, okay. Anyway, so here's the Marsden identity. So you have can we write the function? You look at for fixed y, the function y minus x to the p. How can we write that as a linear combination of B-splines in terms of x, right? And having coefficients in terms of y. And this is Marsden identity. So actually the coefficients are the dual polynomials of the jth B-spline evaluated at y. So so this is, and to show that, I'm not going to go through it, I think, but you can you use the dual recurrence relation to do a recurrent lemma, actually, for this kind of proof, which I give here. There are many ways to prove it, but okay. So so using that, you can now explicitly write any power function x to the k as a sum of B-splines with coefficients Cj, k. So as special cases, I mean, you will, and how to do it, you take the Marsden identity, you differentiate it a number of times with respect to y, and then you put y equal to 0. I mean, you have you differentiate with respect to y and take y equal to 0, and then what's left is some power, x to some power, right? And you get explicitly here from what it is. And so I'm only going to give you a couple of special cases. For if you take 1 x to the 0, you get see the coefficient is 1, so then proves a partition of unity. And if you take k equal to 1, you get the average of the interior knots of the jth B-spline. And these are points which are known as Greville points, which we'll come back to. And just as a couple of other examples, you have a quadratic and cubic case. If you want to represent x squared as the sum of quadratic B-splines, the coefficients are Cj plus 1, product of two the two x's in here. And in the cubic case, you want to x square, you have a sum of those interior knots in this way, and also for x cubed. So then you have explicit representation of any power function in terms as a linear combination of B-splines. And using this now, we come to the control polygon for a spline. So if you have a spline function with coefficient Cj, you can define what's called the control points. These are the points with the coordinates Cj1, I mean the Greville points as the x value, and the coefficient Cj. And then and the control point is then by connecting those control points by making a piecewise linear function. This is known as the control polygon here, and here's an example of that. So, and one of the important things with the control polygon, that in some sense it models the curve, because if you start, if you use more knots, you can use more knots as we come to a knot insertion to represent the curve, and then the control polygon get closer and closer to the curve. So in this way, it sort of models a curve. And not only that, the spline inherits shape-preserving properties from its control polygon. For example, if the control polygon is positive, then the spline function is positive. If the control polygon is monotone, then the spline function is monotone. And if it's convex, then its control polygon is convex, then the spline is convex, which is a very nice, easy way to check, do I have a convex function? You just look at the control polygon for sufficiently fine knot, and then you can get it in some at least a necessary condition. Right? And you have also something called the convex hull property of these parts. Okay, so this brings me to knot insertion. The basic thing is that if you have two spline spaces, SPC and something called SPC check, and suppose the SP, I mean the knot, the one with C is a subspace of the one with there, and it is a subspace if this C check is a knot vector which contains C as a subsequence. And this is and this follows since any piecewise polynomial can be written as a linear combination of B-splines on a suitable knot sequence. And we're not going to technical details about that, but you can always, if you have a piecewise polynomial of degree some p, you can define some knots and some B-splines so that this piecewise polynomial is a linear combination of those B-splines. So that's, you can show that you get this subspace property. So if you increase the number of knots, if you have knots sequence and you add some, you get the bigger space, which contains the original space as a subspace. And so knot insertion was something apart from the Bulgarians and the Romanians, was a formula for inserting one knot was given by Wolfgang Böhm in 1980. And with my co-authors, Cohen and Riesenfeld in Utah, we show how to be able to, an algorithm for adding an arbitrary number of knots. So this is, I mean, my co-author for the lecture notes, we did some improvement on that thing. Okay, so let me just say how can you insert the Böhm's algorithm for inserting one knot. So you're given n plus p plus one knot called CI0, and you define a new knot sequence C1, by inserting a not xi in position nu plus 1 in xi0. So then you know that you have a subspace property. If you have some coefficients di0 on xi, you can there exists some numbers di1 on the not sequence xi1 in this case. And explicitly, the di1s you can compute in this simple formula. So they are equal to di0. The first nu minus p is di0. Then you have a linear combination of di0 and di minus 1, 0 for in this range. And then you have to shift by 1 for the remaining one. And this is, and there are many ways to prove this. Bohm didn't prove it in this way, for sure. And so you can prove it only for using, if it's enough to prove it for dual polynomials. And if you do that, then you can use a dual recurrence lemma to show it like that. I mean, this Bohm's formula. Okay, so that's how to insert one knot. And then you can use that, for example, what is known as Bézier extraction. You can insert, if you insert one knot repeatedly p times, then you can write explicitly the pth coefficient, and then you get at the end only one coefficient left, and it's a product. You can write it as a product of those B-spline matrices multiplied by the original functions. And this is actually the Bohr algorithm for computing the value at the point xi in this case. And if you insert now xi nu and xi nu plus 1 p times each, then you can convert a B-spline representation to a Bernstein basis representation, sort of a local polynomial representation using the so you have certain coefficients here which I won't deal with, and then so then you get this Bernstein basis on the interval xi nu plus 1. Okay. What? B so I, yeah, that's what you get by doing this inverting, yeah, computing. It's a p times at xi nu and p times at xi nu plus 1, and then you get at the end of the day, you get those coefficients bi by using these formulas here. But yeah, this is well known what they are, right? I mean, there are many papers written on that, what BI is, I mean, how you compute it, the algorithm, right? So I cannot give you here the explicit formula for it. Okay, so let me end by just showing the simultaneous knot insertion. So suppose now we have the situation where we have a splines with coefficients Ci, Cj, and we insert several knots sort of anywhere in the whole range, xi1 to xn plus p plus 1. And we get some new coefficient di because we have the subspace property. So what are the di? Well, we know there are linear combinations of the Cj with some coefficient aij. And there's a simple algorithm to compute those the non-zero values aij. Take here is sort of the Bohr algorithm computing f of x as a sum of product of matrices. And you have this C nu I P, which are these p plus 1 coefficients. But now, suppose now we replace these x's by these numbers here, xi check I plus 1 to I plus p, where xi is in nu I plus 1. Then we know what is known as the Oslo algorithm, which is di is simply equal to that. And so that's So for each I, you have to find out where this Xi check in which subinterval of the original Xi it lies. And then you replace or sort of blossom, somebody would say, all the X's into this this sequence here. The X replace all the X's by this vector here, and so this is okay, and so this was always in the 80s. There was a big discussion: what is the most efficient, to use the BIRS algorithm, inserting one knot at a time, or to use Oslo algorithm to insert all the knots simultaneously? And we had big discussions about that. For example, conferences in Oberwolfach on curves and surfaces at Barnhill. And yeah, so this, and so the result is that, I mean, for univariate splines, usually BIRM is better too. But if you get to tensor product B-splines, there is an alternative Oslo algorithm, which is just we first compute the matrix A, I mean those AIJs, using the Oslo algorithm, compute the matrix in each of the tensor product direction, the multivariate directions, and then multiply it by the coefficients. And this kind of matrix vector multiplication is then more efficient than using the original BIRS algorithm. So I guess that's it. R matrices, they were RK had K rows and K plus 1 columns. One took P. Yeah. Yeah, they're growing. So you take the first one, you have K plus 1, so that you can multiply them together. They're rectangular. Yeah. And you can write it out and do more efficient. If you don't like matrix multiplications with many zeros, you can sort of simplify it to explicitly to make it very efficient. The MATLAB, his MATLAB package. Yeah, which was in MATLAB, but which was taken out. Yeah. It was in MATLAB. Yeah. It was in MATLAB, but then they took it out. So it's not. Well, I mean, it's the same. It's the same algorithm. I mean, if you write it out not using matrix products,